Hello, welcome Professor once again to this technology and knowledge sharing session where we'll touch upon variety of different topics ranging from startup ecosystem in India, how to make it successful, talking about aerospace and defense in particular, flying taxis, technological innovation, topics such as avionics, for example, digital engineering thread, and then how to become a multifaceted person doing multiple things, entrepreneurship versus entrepreneurship, and those type of topics. Before we go into this session, I would like to do a short introduction about yourself.
Sure.
Professor Satya Chakravarthy, it's great to have you here. You're a multifaceted technologist emerging from the rigor of combustion and propulsion research at IIT Madras, where you have founded the National Center for Combustion and Research Development, a facility currently that actively drives industry relevant solutions through advanced experimental and computational capabilities. Scaling far beyond your initial combustion work, envisioned and championed spectrum of deep tech ventures and co-founding successful startups like ePlane and Agnikul Cosmos, spanning electric aviation, advanced propulsion we just talked about, and space technologies. Your journey reflects a rare combination of specialist insight, visionary entrepreneurship, and real-world engineering impact. Thank you, and it's a pleasure having you here.
Thank you.
So let's start the conversation with a question related to how interdisciplinary and multiphysics does your work feel today, and how do you expect that trajectory to deepen going forward?
Yeah, so I think the world is always multiphysics, okay? And it's us, we have actually compartmentalized the whole of physics into multiple disciplines. And that's for the convenience of our understanding and our learning and so on. But there's always these interactions between these different physical phenomena that characterize pretty much any product, any technology, or any of these things, right? So you look at a lot of things like a light bulb, you need to worry about like the heat transfer as much as the light and the materials and all of that stuff. So in the beginning, we actually had all these things done in silos. And the interaction was at best one way. You will take like a fluid mechanics problem, then work out the pressure distribution, then put it out into a structural code and all those kinds of things.
That's true.
And then we do a heat transfer at some point and all that stuff. But now today it's possible for us to actually start increasingly becoming more and more interdisciplinary, to the point now we are bringing in electromagnetics into the picture for things like motors, electrochemistry for the batteries, combustion reacting flows anyway is there. That's been happening, so on. So in my case, I used to be doing a lot of combustion work where there was a lot of reacting flows. Then combustion instability involved reacting flows and acoustics together.
Correct.
When we're now doing ePlane, a lot of these other things that I mentioned, aerodynamics, structures, heat transfer, electrochemistry, electromagnetics, all of these things work together. And then we also have to throw in aeroacoustics into the mix when we are now looking at propeller noise simulations when the aircraft takes off or flies overhead and all that.
That's right.
So, and these things have to actually be done concurrently and also in a coupled manner as much as possible, not like in sequence, one after the other.
One after the other.
So the laboriousness of collectively computing all of these things is becoming a lot more. And correspondingly, the compute powers and the software are getting much better and better. It's an amazing time to be in.
That's true. So it's every problem it was done previously, it was done in silos. Now it's mandatory to do it multi-scale, multi-stage, multi-physics kind of simulations, and what better tools, simulation tools to use them and make this kind of digital engineering thread successful. Then if you talk about your own company right now, which is into drones and flying taxis and so on, today's drones are actually increasingly defined by the intelligence of their payloads rather than the structural and aerodynamics integrity. Okay, can you share your thoughts or perspectives concerning this development of payloads and intelligent payloads development?
The reason is we are actually at the cusp of drones becoming commoditized.
Correct.
And once drones are at that particular point, it's as if like the aerodynamics and the structures and all of those things have actually been figured out. And all we are now trying to do is to see how to make it a lot more versatile in terms of use cases and applications and situations in which we can deploy them for multiple different functions. That said, there are multiple different attributes to a drone. A typical drone that's just a multicopter is a electromechanical gizmo. Its job is to actually take power from the batteries and then put it into the motors. The motors are connected to vertical rotors, propellers, and so on. Then you have a flight controller that balances the drone, and then it can then also receive commands to move forward, backward, and so on. Right. There isn't much of an aerodynamics to talk about, but everything has to actually go through a structural simulation in order to be in integrity. But if you now expand that to looking at a lot of the military drones that originally came about when the word drones did not really exist about 20-25 years ago, they are all kind of like aircraft-like, and then it's just that they were unmanned and therefore they were called drones.
Yeah.
They also were making the noise that the word drone itself means, and so these were typically for like surveillance, reconnaissance, as well as for delivering payloads and all that stuff. And they require significant amount of aerodynamics and structural integrity to be worked out, lightweighting with materials and so on. That application still remains. And it's now morphing into VTOLs with vertical takeoff and landing, or kamikaze drones, which actually are suicidal in nature, which means that you have to engineer for less structural integrity to just live that particular life of that flight. And so on. So that's much more interesting and demanding, right? How do you actually decrease the life of a product? Normally you're used to increasing the life of the product and stuff. So the final challenges on drone frontiers is not yet over. It's actually multiplying, as a matter of fact. Yeah.
So some more thoughts on these intelligence and the sensors which are making them, the payloads are so important as part of this new age.
There it's not just the payloads again. It's actually what you do with the payloads comes into picture, and a lot of this is actually happening on the edge. So we do have significant amount of edge computing that we do with processor boards there, right there on the drone, and collecting data from multiple different sensors. Sensors are becoming more ubiquitous. Cameras are more endemic. Very high resolution cameras can actually be miniaturized. You can position them in multiple different angles and so on. You can do precision landing with computer vision algorithms that are driven by camera based spotting of a particular like a QR code for the landing site or whatever it is for security purposes. Similarly, the FPV drones also look at the forward flight. And in all of these things, there is a significant amount of feature recognition by segmentation that comes into picture.
That's right.
And this actually goes all the way to even influencing the flight controller. It's not just about looking at something and then informing the ground station what the drone is looking at, but also trying to control the behavior of the drone.
Absolutely.
In that sense, it's actually vision-based aerial robotics. We actually think of this as part of like a much larger set of developments around the world. That is at the intersection of AI and mechatronics, for example.
It's coming together,
yeah. All of that stuff is actually a lot more easy to do with drones. Things like swarming, for example.
So new applications.
All of these things actually are much more easier to do with drones. As a matter of fact, the next level is things like brain-machine interface, right? So people look at, can I control machines with my thought, right? Tapping my brain waves to navigate machines and so on. And those things naturally come with drones, because with your drones, your thoughts when you're now trying to navigate them is just turn right, left, go up or down, and so on. So those are actually easy to tap from the brain and then communicate to the drone when compared to a lot more complex maneuvers that you need for other objects. So drones are actually sort of like a nice benchmark for you to push the envelope on lots of things.
You have touched upon many topics that are interesting. We'll dwell deeper into
Sure.
these, not just about the payload intelligence and so on. Would you like to introduce about ePlane a little bit and what your future plans are and where you are currently?
At ePlane, our goal is to develop human passenger aircraft, which are essentially VTOLs, vertical takeoff and landing, and preferably all electric from a not only from a sustainable point of view, but also from a affordability point of view. And we are trying to do this for air ambulances as well as air taxis and air cargo applications as well as certain defense applications as well. From the point of view of civilian regulations, these are human piloted, but we have a significant autonomy stack that can fly the aircraft completely autonomous. But from the point of view of carrying human beings in the civilian space, we need to have a human pilot on board. So we sort of represent all of these things, the autonomy features into pilot assist features. And we expect that these will get into air ambulance and air taxis in the next couple of years. We are right now at the cusp of putting out our first prototype for testing in the next month. And subsequently we will do 2 or 3 more prototypes for the certification that we're working on. Plus we'll also put more prototypes on the other variants so that in the next couple of years we should actually have about 3 variants certified.
Great. All the best wishes
Thank
for this. So again, just going back to that payload intelligence, if you look back, there was a time when optics and photonics were purely scientific fields.
Yes.
And today they have evolved into fully applied science and engineering domains. How do you perceive this and personally resonate with what you have explained?
Right. So the whole idea of most of this technological developments is to try to see how to reach to the common people.
Correct.
Right. And there are 2 aspects to that. One is to ruggedize it, miniaturize it, and make it affordable and so on. The other one is to commercialize it. That means that you should actually find lots of applications in which you are able to insert these payloads, typically the cameras and so on. So now today, for example, every cell phone actually has at least about 3 cameras.
Absolutely,
right? Some of them in the front, some of them in the back, or combinations of and all that stuff. Which means that in any room you will actually have literally about a dozen cameras.
Exactly.
Now imagine that these things can actually sit on top of drones or can actually sit on top of aerial vehicles, or it could be on driverless cars or on satellites or what's called as high altitude pseudo satellites and so on. There is just a lot of things that can be done with the images that are taken and then slap AI into it, right?
Absolutely.
So the point is, when I grew up as a grad student, AI was actually part of what's called as theoretical computer science, which means that they were not even sure whether that's actually going to see the light of day in any sense of the word. They would actually be arguing whether AI will essentially mean that a computer has intelligence, computer has consciousness, is it like a human being, all those kinds of things. Those questions still remain, but we have actually gone to a lot more practical side of AI, where we are seeing immediate applications based on linguistics, language processing, and all those things, right? So, and the same thing can actually be applied for visual data. When we now combine visual data with language, the kind of intelligence that we are actually trying to sense is very close to human, because humans are visual species as well as they describe things in words. And how do you combine visual and word descriptions is where we really are in the forefront. And now we are beginning to see the AI, with the help of these sensors and with the language that is informing it, are becoming at very close to what humans can do, or even better many times, right? So this is a potent instrument in the hands of all the technologists that can make use of it for any application, as a matter of fact.
Actually gone into the next question, where we was already conveying the message how to use AI for digital engineering, development of products, or for that matter, digital engineering for AI.
Yeah.
I think it's both ways these days. How do you generate the data for simulations and then simulations for AI, right?
True. So that's important, because design can be actually adopted with AI, so that we can actually cut down multiple cycles of design iterations, right? And AI can kind of inform us on what could be the next modification in the design that will be a lot more fruitful.
Right.
In aerospace, we take that with a pinch of salt. We basically kind of take it as an aid. We still have to actually go back to physics-based simulations on whatever AI informs us. So we, on the one hand, we actually have like a lot of data stack on multiple simulations that allow the AI to inform us, but what the AI informs us back has to be validated with physics-based simulations back again to check whether AI is right or it's actually hallucinating or any of those things. Yeah.
Right. I mean, AI is part of, I think, AI first, digital engineering first with AI. I think that's the future. Just one more question related to this AI for deep tech versus AI for shallow tech. That comes always as a part of our thought process in the deep tech industry we are in. What are your what's your take on transferable learning between the two, and what do you see as the key differentiators between the shallow tech and deep tech?
So in the case of shallow tech, it's possible for you to actually get a lot of data that can be used as training data sets for the AI, because typically it's all about just applying it to multiple different customers and uses of the product and so on. And therefore you have lots of data that comes at you, which can be fed into the AI model, AI engine, and so on. Whereas in deep tech, the problem essentially is that the product that we are developing is fairly precious. So that means that you cannot actually do lot of simulations or get lots of data with for these, because these are like, for example, let's say I'm making a plane that's fairly large, right? The domain itself is actually so large. The number of cells that I would use, the mesh sizes, the simulations that will happen will take like several days, and we will not be able to actually generate the kind of data that's required for us to train a normal plain vanilla flavor AI engine like what you would do in shallow tech. So instead, we need to actually have Gen AI models that are intelligent enough to be able to predict what should actually be the design iterations that are smart for minimizing a certain cost function with very little data. And that's actually at the edge of AI itself as we speak today, where we try to liken the present age AI, the Gen AI that we are looking at, as learning with minimal data sets, right? So like how a child grows with just minimal inputs and then it picks it up on the fly.
Absolutely right. That's an emphatic statement, considering, I mean, where we are using the simulation tools, you're actually building the foundational models which are based on simulation knowledge, and then combination of generative AI. Then now you add the agentic workflow. So I think that's the future, which has to be within our product development. Now, talking about the AI virtual product development and so on, we briefly touched upon digital twin, physical and digital worlds coming together. In what ways are digital twin poised to minimize field trials in your current work?
So the thing about digital twins is actually at 2 or 3 different levels of fidelity, right? So high fidelity digital twins will require lots of physics details, right? So you now then get as close to physics-based simulations and model-based twinning, and that may not actually work real time. And that means that we can probably check the larger performance goals for the machine that we are trying to develop the digital twin of, but we will not be able to actually do this for things like, for example, health monitoring, those kinds of things that are routine during the operation of that machine, right? And that would probably require us to get into low fidelity models that mimic the actual operations as closely as possible. And there again, AI comes into picture, right? Where an artificial intelligence informed model, right, that allows for the operation of the machine to be mimicked very well, instead of actually having to have the full physics going through. So these are areas where we can use digital twinning in multiple ways. First for design and design evolution, but second for operationalizing lifing predictions and all that stuff without having to do the physical testing of the hardware.
Right. And you touched upon the right points, Professor. At what level of digital twin we are talking about, and where it will be used or applicable in the field trials.
Yeah.
That's great. Okay. Then talking about field trials and how we are doing the physics-based simulations, what's the relationship you see between physics-based simulation and functional safety?
That's a question of actually shoring up on reliability and designing with redundancies, right? So many times when you now actually look at functional safety, it has to be factored in at the design level. So in aerospace, for example, we have this concept of design assurance levels. That means that we should be able to assure at the design level what is the functional safety of a product without having to develop the product, go through the testing, and then come back and say we have tested it enough to be able to tell you that it's actually functionally safe.
Correct.
Right? So from that perspective, it's actually more of a design problem rather than a testing problem. And of course, you need to actually test it to be able to validate your design. There's no avoiding the testing, but these things actually are. I mean, the functional safety part is starting from the design stage. So we should actually be able to factor in functional safety from the view of building redundancies and then developing reliability of the components and the subsystems.
Great.
Yeah.
So, I mean, in terms of just going into the topic of approval process, how that is coming up, Professor?
Yeah, so the certification process actually is fairly well laid out. And the process itself actually has built into it what is called as a means of compliance. So we need to be able to agree upon with the regulator what is the means of complying to certain standards that the regulator has set. And the regulator is actually setting these standards in terms of things like reliability, design assurance levels, all of those kinds of things for multiple different systems. So there's like a DALE which is actually critical. So it has to actually withstand catastrophic failures and so on. Whereas DAL B is like less critical and DAL C is even less critical and so on. So there is a hierarchy of multiple subsystems that work together, of which some of them are the most critical ones, some of them are less critical ones and so on. All of these are put together at a design level, so we are able to actually show how we are fulfilling the criteria of the regulations.
Right.
But we also actually have a means of compliance by which we say this being the design, I want to show compliance to the regulations with this design based on these tests to validate the design and the design assurance that we are giving on the safety. So we go through that process. It's a combination of component level ground tests as well as flight tests of the full bird over time, and like you have to clock a certain number of hours, and then you also have to evaluate what are the mean time between failures for each of these components. That adds up to what is the DAL levels for these different subsystems. So there is a lot of intricate level of work that needs to be done to show the means of compliance.
Hopefully the digital engineering thread or workflow which you're developing using simulations plays an important role.
It does.
Yeah.
So today's world, digital simulations based results are actually a significant part of the validation.
That's right.
Right. So and then of course it has to come from proven simulation software that have actually developed a pedigree of having done this with multiple different other larger aircraft and so on. The kind of eVTOLs that we do are kind of the new kid on the block. It combines drones or helicopters with fixed wing aircraft. At the fixed wing or the helicopter level, they are kind of smaller than aircraft that have gone through simulation based certification.
Correct.
But still this particular combination, we can accept simulation based certification up to a certain level, but on top of which we go through flight tests and the component level ground tests. But simulations do form a very important part of the design validation.
Great to know that. Just again, your perspective on how impactful are mission level simulations in shaping system design and clarifying overall system performance.
Yes, that ties with the first question that you asked on multiphysics.
Right.
Okay, so when each of these systems or subsystems is designed with certain amount of physics, factored in, it's only the mission level simulations that bring in all the physics together, and that's where a digital twin will be super useful.
Correct.
So all of these things are kind of like they all go together. The questions that you have asked in performing mission level simulations, right? And the mission level simulations, again, as I said about the digital twins, is it actually for evaluating the performance of the aircraft, or is it actually about operation of the aircraft, right? For
Component, yeah.
like functional health monitoring and those kinds of things,
That's right.
or prognostics of fault detection, and so on, right? So multiple objectives that can be met with mission level simulations. Yes.
Again, that's great to know that how the simulations are helping it from component level, system
Absolutely.
level to the entire mission level. We talked about system of systems, digital twin, AI. Then the next one is all about nowadays, of course, software-defined systems is there, but the major one people are talking about is the chip or the semiconductors.
Right.
Right. I mean, it's about a component to systems we talked about. It will be called as chip to system. So semiconductors is becoming an important part in the products we develop. So the technical trends that have recently driving this increased global emphasis on semiconductor and silicon proliferation, Professor.
Yeah, I mean, semiconductors have actually kind of been flooding pretty much a lot of things that we do.
Right.
Primarily because a lot of these systems are actually becoming smart, which means that decisions are being taken on board. And that means that we need to have processors that are built into pretty much every system or every subsystem, and so on. There are local, for example, in the case of aircraft, you have battery management systems, battery thermal management systems, energy management systems between multiple different battery packs that are informing or delivering power to multiple different power this thing, what do you call, loads, right, like motors and propellers. All of these actually have to inform the flight controller. The flight controller, again, is a triple redundant software system, and then you need to be able to actually do voting between these three of them, and they could be dissimilar. So everywhere you actually will see that semiconductors play a role in something like an aircraft. Cars, for example, are actually now being seen as computer on wheels. The earliest of autonomous vehicles is actually rockets, and rockets have always had, right from day one, they have been actually having an onboard computer that informs how the vehicle has to be controlled with gimbaling of the rocket motors and all of that stuff. So everything is actually a decision making point, and that requires a processor on board, and that requires semiconductors to be there, and so on. So now that is actually becoming a lot more commonplace with a lot more smart systems around.
Same thing, in the last 4 or 5 years, being a mechanical engineer, I had to learn about a lot of these chips, and
indeed,
and in terms of learning better with our simulation solutions. So just going in a little bit of off topic, because you come from that highly engineering background, and then some intriguing engineering applications of complex numbers with the systems we are developing these days. Any?
You mean like the real and imaginary part, complex numbers? Yeah, I mean that's actually very, very commonplace. So wherever you actually have to deal with a magnitude and a phase, right? So it's a very easy way of representing it with complex numbers.
Correct.
And most of the time you'll actually have to deal with any transient phenomena, and all phenomena actually are transient. It's just that for the ease of handling, we then we simplify it to a steady state.
Correct.
Simulation artificially, but the moment you actually now relax that particular assumption and then look at the transients, you have to worry about like phase delays between processes and stuff. And when that happens, you have to keep track of not only magnitudes of proper quantities, but also the phase delays between them. That's where a complex representation becomes a lot more useful. And this is definitely true for like control algorithms for vehicles, things like acoustics, all other wave propagation, vibrations, every time dependent phenomena definitely has and then of course the Fourier series representation of those. All of that stuff actually has a huge complex representation.
Okay, great to know that. We'll move to a new different topic on what we are doing is all for sustainability of the world we live in. Can you please tell the ethos of sustainability which is driving the technological innovations?
So the thing about sustainability is that it's my feeling that that if you look at the history of the world, the problem of the planet getting warmed up, the global warming and the climate change and all that stuff is relatively recent in the last few decades, if you will. Where if you look at actually the carbon dioxide emissions and the global temperatures, they're all kind of like going through a very steep curve in the last maybe 100 years max to max, but definitely lot more in the last, progressively getting steeper and steeper through the decades, right? So we now are actually having to dial back and then say, hey, is it possible for us to become more carbon conscious, right? Decrease the carbon footprint. But the point that we have to ask is, can I actually think of something from basics, right? If I were to actually develop a new product, new technology, something that is from scratch, like let's say for example an electric eVTOL aircraft, which is supposed to actually solve the problem of urban congestion, right? Traffic congestion and so on. But when I'm making this, I want to be consciously sustainable as a choice. And you do that primarily for actually making it more affordable, rather than simply saying that I'm doing this for the sake of sustainability.
Absolutely.
Right? So the summary there is, you think sustainability first. Don't even have that as a choice, and do that for the sake of affordability rather than for the sake of sustainability itself.
Yes, sir.
Then you are actually bringing all the objectives together, in which sustainability forms a central part, right? Instead of making it a separate goal by itself.
Very well said, Professor. I mean, what we learned is about achieving more with less. Always thinking about 3 Ps, right? People, planet, profitability.
Absolutely.
I think that's well said from you.
Correct.
That it
so the
should
way
be
I say it is
sustainability
that,
first.
So you not only actually think about the planet, but you also think about the pocket. So you have to actually look at both of them together.
And nicely said. And again, talking about profit and what we are currently doing, what's your perspective on can there be a better technological direction for companies like us to contribute earnestly through their CSR initiatives as well?
Correct. So today, for example, at least in India, the rules are that the tax regimes and all of those things are now favoring a lot of deep tech startup investments to count for CSR, right? And the kind of CSR grants that you have, you could actually look at setting up venture funds that can get into seed funding. There are rules about CSR that it should not be looking at your requirements, right? That is, you should not actually drive your profitability. It has to be more for social good.
Right.
Social good actually can be achieved by spending CSR money on deep tech startup funding. And deep tech startup funding is, some of them are considered to be like moonshots, for example. So you don't know whether it's actually going to come out or not. But unless you actually fund them, you will not know. And that's how a society explores itself to its maximum.
Correct.
And what better way to actually put CSR to good use than this, right? So that the entire society, a lot of youngsters, a lot of new ideas, all these things are fostered. So I would believe that CSR has to be utilized, towards more R&D that's leading to translational research and startups that are of the deep tech nature. Lab to market transitions. These are all things where CSR can play a huge role.
Very well said again. So again, we're staying to the same topic. For doing all this stuff, skilled manpower is highly required. Okay, so touching upon, for sure, skilled manpower is required with all this technological knowledge is there. But what's your take on the role of academia in earnestly and effectively teaching this entrepreneurship? Or are we living in a time when academia is overrating the celebration of teaching entrepreneurship? Well, so it's intrapreneurship versus entrepreneurship.
Understood. See, academia, for a large part, right, at least in a technological university, like let's say institutes of technology and stuff. So we are more interested in imparting knowledge on the technology side of things.
Right.
The utilization of technology by means of startups by the students and or combination of students and faculty is what leads to entrepreneurship. And the academic ecosystem celebrates that by default, instead of actually saying entrepreneurship is better than entrepreneurship and stuff. Where an entrepreneurship is actually important is in large organizations. So large organizations will have to understand that they need to foster entrepreneurship so that they can actually be nimble, and they can pivot to new markets and new applications. And it's not so easy, because if you're a very large organization, you're always looking at what's the margins that you can clock and what's the profitability of a certain effort that you're taking and so on. And you always look at return on investment, right?
Correct.
So you basically say, I'm actually such a big company, I'm not going to worry about like the small margins that I can clock with getting through with this innovation, right? But what they don't understand is that you will actually start with very small margins to begin with new innovation, but that will actually grow over time, and it will actually swallow what your original enterprise itself was.
Right.
And if you don't wake up and smell the coffee internally, somebody else will actually come and swallow you.
Absolutely.
Right? So the entrepreneurship is something that is actually meant for large organizations to stay nimble and say, wait a minute, I have to actually earmark some amount of my effort into fostering entrepreneurs who will develop technologies that may look like a very nascent stage and are going to clock smaller margins. That doesn't matter to me at all, but I want to have that grow so that when on a rainy day when my old technology is becoming obsolete, my entrepreneur is the guy who is actually going to become the poster boy.
Nicely said. That's a balance. Yeah, thanks. Again, staying between us and the academy and skill development topic, actually, how important is avionics in the current age, and in the current BTech programs today? Do you feel the faculty bring in enough real specialization to offer it as a core competency, or rather than just an add-on?
Well,
It
avionics,
could be other topics as well.
right? So avionics, for example, is actually in a state of flux, right? So if you look at a lot of other electronics other than avionics, they all have gone far ahead in terms of miniaturization and multifunctionality and so on. So you can actually pack a lot more in a given chip itself for what you can achieve, for the electronics. Right. But the problem with avionics is that you need to actually certify it, right? You have to go through certification, you have to worry about robustness and so on. So this seems to be actually making inroads in space technology, where the certification standards for unmanned rockets is not that high, and it's possible for you to actually try out things like different communication buses and just as an example, right, which are a lot more commonplace, like for example Ethernet switches and or Wi-Fi or any of those kinds of things. But for manned aircraft, which are like civilian, there are stringent standards that prohibit you from using like run-of-the-mill avionics to be put on the plane, no matter how many redundant systems you can actually pack into it and compare to like a certified product. So that means that the burden of having to certify new electronics as avionics lies on the people who are actually trying to innovate, and that's a little bit of a hurdle. So what we need to do is to sort of have like entrepreneurship, right, where you develop the commercial grade electronics into avionics systems.
Right.
I don't think that can be taught, right? And that is not really something that is the stuff of classrooms, right? So and that's something that has to actually be picked up by avionics companies or aircraft companies. Yeah.
Again, very well said. Yeah, hopefully we'll find a solution to these very important topics. True. Which is massively required for companies like us to immediately utilize this. Yeah. So IIT Madras Research Park, where you have originated from, has seen impressive industry academy outcomes, one of the very best successful outcomes from India. What do you make of similar efforts at other IITs, which is really required at other IITs as well? No,
so IIT Madras is at the forefront of all of this, and then they do look like they are kind of miles ahead of others, and that's because, so you have this phrase called success breeds success, right? Nothing succeeds like success and so on. So it's all like a multiplier effect. And then there is also like a tremendous focus, and there is a culture of promoting or valuing translational research that can lead to lab to market transitions, and so on at IIT Madras. Probably the rest of the country's academia are a little bit slow on the uptake perhaps, or whatever it is, but they are not far behind, right? If you look at an IISc or an IIT Bombay or an IIT Delhi or an IIT Kanpur or any of those, so they have their fair share of entrepreneurship outings. And now entrepreneurship is actually penetrating deep into the tier 2 colleges like the NITs and other prominent state universities and so on. I think it's actually more to do with the generation. It's less to do with the institution. So we have to actually give the devil its due, right? So youngsters actually see opportunities. There are VC funding for seed money to translate to, let's say, growth funds within about 18 months if they have a good idea. So all of these things are actually not institution specific. Good. They could actually be like nucleated in these institutions, but it actually spreads like wildfire pretty quickly.
Yeah. Okay. Your thoughts on, should ISRO consider a dedicated platform similar to NASA spin-off to actually channelize these defense-related R&D into scalable civilian technologies?
Well, see, NASA does not have the burden of being answerable to the rest of the world, whereas ISRO in the past has actually been subject to scrutiny even by the US government in not doing anything that's of defense import. Although most of aerospace actually has dual use purpose, and everybody understands that, everybody knows that. ISRO tries to avoid doing anything for defense or spin-offs in defense and so on explicitly. That is their mandate. They are supposed to be looking at peacetime space applications, right?
Correct.
Peaceful space applications that are more of civilian nature. But nothing stops the rest of the country to actually pick it up from there and then put a defense flavor to it and pick it up from there. DRDO has actually been sort of segregated from ISRO in terms of like interactions and stuff. But there are lots of other defense agencies and startups that are there that can actually take off these spin-offs from ISRO's applications.
So it's basically working on that.
So it is possible. It is possible to be done without having a formal structure. Yeah.
Okay. So one last question, Professor Satya. Going from passion to paycheck and from vision to mission, what's your take on navigating that journey with diligence if you were to give both a philosophical and a scientific spin?
Right. So that's actually somewhat, it's very paradoxical, right?
Correct.
So when you're passionate, right, you stop being analytical because passion takes over and you right. But you need to have this the mind intellect balance where you actually think through a problem and then say that this is what needs to be done, right? This is a solution, and you fall in love with the solution, right? And then develop the passion for pursuing this solution to implement it.
Correct.
Right? That kind of a clear way of actually doing this, where a intellectually informed decision to be passionate,
yeah.
right, doesn't happen to a lot of people, right? But that could be consciously cultivated. Yeah.
Very great.
Yeah.
And it's been happening with like where you have been successful.
Yeah, agreed. Yeah, I would acknowledge that. Yes.
So, Professor,
thank you so much.
Professor, pleasure to have you here, where we have talked about variety of different topics. Indeed. Ranging from multiphysics to digital twin to entrepreneurship to how to get to that successful companies.
Yeah, sure. Yeah, thanks
pleasure
a lot. Thanks
all
for
the best for your
Indeed.
future. Yeah,
pleasure. Thanks so much.